bubble sort. So today we'll be learning about quick sort and merge sort in detail with suitable examples. So we'll be learning what are the advantages and drawbacks of these two sorting methods. So we'll move on to the lecture. So those who didn't join in the previous class, so you'll have to know what is meant by sorting. So sorting is nothing but arranging the data in some given order, either it be ascending order or descending order, and it is with respect to either numerical data or character data, right? So what is the requirement for sorting is all data processing requires the data to be in some order, right? For example, arranging of the marks of the students. So if it is arranged in a random fashion, it is very difficult to search a particular mark. Or if we have some books in a library, so picking a book in the library is not so easy if it is not arranged in some order. So these are some of the real-time examples and the requirement of why do we need to do some sorting with the data. So when you sort the data in some order, either it be ascending order or descending order, picking up the data or retrieving the data or searching or finding a data from the list becomes easier, right? So the main categories of sorting, there are two categories as we have discussed earlier. It is internal sorting and external sorting. So with respect to classification of sorting techniques, we can classify it mainly based on internal and external sorting, where internal sorting is further classified based on its time complexity, like with respect to linear time and polynomial time. Right, again, polynomial time is categorized into simple and sophisticated. So in the previous lecture, we have seen about the algorithms with respect to simple complexity with order of n square, namely the insertion sort, bubble sort, and selection sort. So in this class, we'll be learning about two important algorithms, namely the quick sort and merge sort, whose time complexity is order of n log n, right? Okay. So to know or to refresh what is internal sorting, so if the list that you're going to sort is small enough, then the methods that we use here, we call it as internal sorting methods. Here the entire sort can be carried out. Some of the examples of internal sorting methods which I have listed below. One is selection sort, insertion sort, bubble sort, quick sort, merge sort, and heap sort. So in this lecture today, so we will be learning in detail about quick sort and merge sort as I have discussed now. Right. So first we'll be learning about quick sort. So this is a very popular sorting method. So the name comes from the fact that it is very quick and faster to sort the given list if we follow this quick sort algorithm, right? So it is also known as partition based algorithm. So where, or we also call it as partition exchange sorting algorithm. So this normally follows the strategy of divide and conquer, right? So we partition the list based on some pivot element and then we try to sort it. So before learning with an example, so first you have to know what are the steps you have to follow to perform this quick sort. The first thing is you have to identify the pivot element. Then you will be trying to move this pivot element to its correct position. So once when you move it to correct position, so it will be in some position where all the elements left side of the pivot element is called as partition 1 elements, and whatever elements be the right of pivot, we call it as partition 2. So first step, we have to identify the pivot element, then find the exact position of the pivot element in the list. So once when you find the exact position of the pivot element, so it is known that all the elements that is left side of the pivot element, we call it as partition 1, and all the elements right side of the pivot element, we call it as partition 2. So you have to know that in partition 1, all the elements left side will be less than the pivot element, and partition 2 will contain the elements which are greater than the pivot element. So this procedure has to be recursively carried upon each partition until the entire list is sorted. So I suppose that you understood it. So primary step is selection of pivot element. Then you have to move it to its exact position. So once when you move it to its exact correct position, all elements on the left will be less than that element. or we call it as partition 1. All elements to the right of the pivot will be greater than the pivot element. We call it as partition 2. So recursively, the same procedure has to be applied for each partition until the entire list is sorted. Right. So we'll come up with a simple illustration. So consider there are some students in a class and the teacher is asking the students to like form a line according to their height order. So what will be the better solution? So what are the solutions? Yes, there are two possible solutions that I can suggest. Either the teacher herself or himself can arrange all the students in the class. The second solution is the students can arrange themselves, right? So which solution will be better? The first solution will be quite difficult because the teacher has to identify which student is smaller in the class, which is the tallest one, which is the middle tallest, and she or he has to arrange the students, which will be some tougher solution. But the second solution is the students can arrange themselves, because if there are some 60 students in the class, a student who is very shorter will know that he is the shorter one in the class. So definitely he can come and stand in the uh, front where some sorting is done there. And on the other contrary, for example, there is a very tallest student in the class. He himself will know that he is the tallest person in the class. So he can go and stand on the behind, right, at the last. So what will be with respect to the other students? So what they will do, they themselves will come, stand in the middle, adjust among themselves, and they will sort according to the height order. So this is one simple illustration of quicksort. So similarly, quicksort is very faster. It's quite faster like this. The elements in the list can be arranged among themselves, whereas easily the sorting can be done. Right. So consider this list. So in this list, if you see here, 2 I consider it to be, for example, if I have taken 2 as the pivot element, so I say that 2 is exactly in its correct position because that is the smallest element which has to stay in that place. So if you see, whatever elements is less than 2 has to reside on the left side. So there is no element less than 2, so there is no element on the left of 2. What about the other elements on the right side of 2? So every element of 2 is greater than 2. So it resides on the right side. So see this example. Here if I see, for example, if I consider 10, so all elements less than 10, if I consider 10 as the pivot, so if you see here, all elements less than 10 are on the left of 10 and there is no element greater than 10. So 10 is exactly in its correct position. See this example. For example, if I consider 7 as the pivot element, so what is the strategy here? All the elements less than 7 should be on the left of 7. All the elements greater than 7 should be on the right of 7. So if you see here, I say that 7 is in its correct position because you see here 5, 2 and 3 are less than 7. It is not required that the elements should be in sorted order, provided it can be in any order, but the condition is when I move a pivot element to a correct position, all the elements left side of it should be less than it and all the elements right side of it should be greater than it. Right. So now we'll see an example and we'll learn how quicksort works. So consider I have taken a list of 10 elements. So n represents the number of elements in the list, u represents upper bound, l represents lower bound. Okay. So this is the list which I have taken. So there are 10 elements. So how do you index this list? Starting from 0. So I start the indexing from 0. So indexing starts from 0, goes till 9. So totally there are 10 elements. And the name of the list I call it as K. Okay. So in addition, we need 2 more indexes here. So I call it as L. L is nothing but it represents the lower bound. So what is the lower bound in this list? 0. Because since the list varies from 0 to 9, so the lower bound is 0. And what is the upper bound here? Upper bound is 9, which is the last index of the list. So the initial index is 0, the last index is 9. So lower bound is 0, upper bound is 9, right? So here we need 2 variables to iterate into this list. So one variable I call it as I and the other I call it as j. So the iteration of I starts from the first position. So initially you have to set I is equal to L plus 1. So initially L is 0. I have to start the iteration from the first position element. So what will be I? I is equal to nothing but L plus 1. So I will be pointing to position 1. And J has to point to the last position. So what is the last position here? It is pointed by 9. So last position is pointed by U. U is nothing but the upper bound, which is pointing to the index 9. So J will also be pointing to U, right? I hope that you can understand. So what is the work of I is you have to iterate and move I onto the right side, and you have to iterate and move J to its left. So every time you have to increment I, and every time you have to decrement J, right? Okay. So the work of the ith element is, or the I loop is, so what it has to do is it has to find the greatest element compared to the pivot element, and the work of J is it has to identify the lesser element compared to the pivot element. So in this example, I have selected the first element to be the pivot element. So what is the first element here? 42. 42 is the first element, that is the element in position 0. The element in position 0 is called as the pivot element here. I've taken that as a pivot element. Now we are going to find what is the correct position of this 42 in this particular list. So that is our objective first. That is the first step. So you have to first fix the pivot element. Then we'll be trying to move the pivot element to its correct position in the list, right? So what we have to do is you need two loops. One is I and the other is J. So every time you have to increment I and find out if there is any element greater than the pivot. So because greater elements has to be moved to the right side, and less elements, smaller elements has to be moved to the left side. So that is our ultimate objective. That is, we have to first find out the exact position of the pivot element on the list, such that every element left side of the pivot should be less than that, and every element right side of the pivot should be greater than that, right? So that's what we are trying to do. So you have to understand. So I loop is nothing but which is a variable which is going to find the value that is greater than the pivot, and J is the variable which is going to find out a value which is less than the pivot. So the pivot value what we have selected here is 42. Now see this. Now we'll come with the I loop, right? So I is pointing to index 1. So what is the value here? The value here is 23. 23 is less than the pivot 42. So there is nothing to do with this. So you have to just increment the loop by 1. Right? So increment I by 1. So since 23 is less than 42, you can just increment I by 1. So now I becomes 2. So now it is pointing to 74. So what is 74 when compared to 42? 74 is greater than 42. So now I loop stops here, right? So the variable I stops here. Now we have to iterate the J variable. So what is the work of the J variable is it has to find an element which is less than the pivot element. So now J is pointing to the 9th position. So what is the element in 9th position? It is 87. So compare it with the pivot. What is the pivot? Pivot is 42. So 87 is greater than 42. So there is nothing to do with this. So you just decrement the J by 1. So when you decrement J by 1, now J will be pointing to index 8. So what is the element there? 99. So 99 is also greater than the pivot 42. So there is nothing to do with this. So just decrement the loop by 1. Now J comes to 7th position. So what is the element there? 36. So 36 when compared to pivot 42, it is less. So now J stays in this position. So we have found a place where we have to make I stay in a position and J stay in a position. So now what you have to do is you have to just swap I and J. Okay, now see here the condition K of 2. So what is there in K of 2? K of 2 is 74, which is greater than the pivot, that is key 42. So I stops at 2, and K of 7 is less than the key, that is 42. Hence J stops at position 7. So now once when I and J stops in particular position, you have to swap I and J. So before swapping, you have to check a condition whether the value of I is less than J or not. So only if the value of I is less than J, we will perform swapping. If the value of I has crossed j, that is, if the value of I is greater than j, you cannot swap. In that case, we will identify the exact position of the pivot. I hope that you understood this initial step of this particular quicksort algorithm. So I'll just have a quick look on this. So first step is you have to identify, or you have to select a pivot element, try to move to its correct position, right? So once when you move to its correct position, you will know that all the elements left side of the pivot will be less than that, and all the elements right side of the pivot will be greater than that. Okay. So in this example, as I told you, we have taken a list of 10 elements where the index varies from 0 to 9, and we have lower bound and upper bound. Lower bound is index to 0, that is points to 0. Upper bound variable points to 9, and I variable starts from 1 and j variable starts from 9. So I told you what is the work of I variable. So I is nothing but we'll be iterating the I value one by one until we find a greater value compared to pivot. So when, for example, here initially I is pointing to 23. 23 is less than the pivot 42. So just increment I by 1. So now I points to the second position. So what is the value in second position? 74. 74 is greater than 42. So I stops there. Now we have to start the iteration with j. So j is initially pointing to 9, right? So what is the value of j? It is 87, which is greater than 42. So there is nothing to do with this. So what you have to do, you have to immediately decrement j by 1. So now j comes to the position 8, where you see that the value is 99. It is still greater than the pivot 42. So you just decrement it. When j comes to 7, it finds that the value is 36, which is less than the pivot 42. So now I and j stops here. And what's the condition you have to check is whether if I is less than j or not. So if I is less than j, you have to swap. So that's what I have written here. So if you see here, we have swapped those elements. Since I is less than j, so I is 2 and j is 7. So I is less than j. So we have swapped 74 and 36. So 36 comes to 74. So 36 comes to position 2 and 74 goes to position 7. Right? Okay. So now I is pointing here and j is pointing. I is pointing to 2 and j is pointing to 7. Right. Now we have to again start the iteration process. Increment I by 1. And what is there in I now? The value 11. So it is compared with 42. So since it is less, there is nothing to do with this. So I has to find a value which is greater than the pivot, right? So simply increment I by 1. Now I becomes 4 and now it is pointing to 65. So if you see here, 65 is greater than the pivot 42. So I stays in this place, right? Now we have to do with j equal to 7. So decrement j by 1. Now what is the value of j? J is equal to 6. So it is pointing to index 6. What is the value here? 94. So 94 is greater than 42. So there is nothing to do with j. J has to find an element that is smaller than the pivot, right? So since 94 is greater than 42, just decrement j by 1. Now j comes to this place. So the value here is 58. So 58 is greater than 42. So there is nothing to do with this. So simply you decrement j by 1. Now j comes to this place. J is also pointing to 4. So it is now pointing to 65. This 65 is also greater than 42. So what you do is simply decrement j by 1. Now j is coming and pointing to 3. I've mistakenly given it as 6. It's not 6, it is 3. So j is pointing to 3. So what is the value there in this position? It is 11. So is it less than 42? Yes, it is less than 42. So this pointer stays here. Now we have to check a condition. So what is the condition I have told you? I value should be less than j. So in this case, I is not less than j. Here j is equal to 3. It is not 6. So I is not less than j. So you cannot swap I and j. So in this case, what you have to do is you have to exchange the pivot element to j and j to the pivot, right? So that's what we have to do. So I see what I have written here. K of 4 is greater than the key value. Hence, I stops at position 4. K of 3 is less than the key value. Hence, j stops at position 3. So since I is greater than j, so here the value of I is 4, value of j is 3. It's not 6, it is 3. So since I is greater than j, so I is greater than j, you cannot swap I and j. So if this is the case, you have to swap the pivot element with the jth element. So what is the pivot element? 42. What is the jth element? 11. So we are going to swap both, right? Okay, when you do the swapping, now 42 has moved to which position? Third position, and in the place of pivot we have moved 11. So now we have found that the correct position for the pivot element 42 in the list. Okay, so see here, we see this example. Now I have moved 42, so I have taken 42 as the pivot element. I have moved 42 to the correct position in the list. So if you see here, we take 42, all the elements on the left side are less than 42, right? 11, 23 and 36 are less than 42, and all the elements on the right side of the pivot are greater than 42. So what are the elements on the right side? It is 65, 58, 94, 74, 99 and 87 are all greater than 42, right? So the elements less on the left of 42, I call it as list 1, and the elements on the right of pivot element, I call it as list 2. So either you can call it as partition 1 or list 1 or partition 2 or list 2. I hope that you understood, right? So now the same quick sort algorithm or the operation has to be applied to both the partitions. That is, list 1 also you have to apply, list 2 also you have to apply separately. So if you take list 1, it is not that all the elements will be in sorted order. All the elements in the partition will be in the sorted order. It may or may not be in the sorted order. You have to recursively apply the procedure and sort them. So first consider list 1. So here in list 1 now, what is the first element here? It is 11. So I will consider 11 as the pivot. So L will be pointing to 0, which is the lower bound here. And what is the upper bound in list 1? It is the element in position 2, right? The first element is in position 11 is in position 0, 23 is in position 1, 36 is in position 2. So the lower bound is 0. Upper bound here will be now 36. That is, J will be pointing to the element in the second position. I will be pointing to the element which is L plus 1, right? So always I equal to L plus 1. So that is our algorithm. So I equal to L plus 1. So I will be pointing to the element in first position. Similarly, you have to iterate. So when you iterate, you can see that. So you'll be iterating I by 1. So it is 23, which is greater than 11. So I stops here in this position. Then J will be pointing to 36. So 36 is greater. So you decrement J by 1. So in that case, J will be pointing to 23, right? So which is also greater. Again, you decrement J by 1. So if you check here, the condition is false. 11 is not less than 11. So now both L and J will be pointing to the same element. So you have to swap there itself. So there is no exact swapping here. 11 is swapped with 11. So already it is in sorted order. So it is 11, 23, 36. It is sorted. So this will be the quick sort on list 1. Now you have to apply the quick sort to the right side. That is the list 2. So how will you apply it? So here till 42 it is sorted. Now I have to identify the pivot element. So in list 2, which is the first element, 65 is the first element in list 2. So it is in position 4, right? So L will be equal to 4. What is I? I is nothing but L plus 1, right? So I will be pointing to 5th position. Okay. What is J? J will be pointing to the last position. I hope that you understand. So in list 2, which is the first element, 65 is the first element. So it is in position 4, right? So starting from 0, if you check it out, 65 is in position 4. So L, you have to select it as 4. And what is I? I is nothing but L plus 1. So I will be pointing to 5th position. And what is J? J will be pointing to the last element, which is the 9th position. Now the same process of quick sort you have to do, right? So what we do? So first I will be pointing to this. Now you check whether it is greater or less than the pivot. So in this case it is less. So you iterate I to the next position. So now I becomes 6. What is the value here? 94. 94 is greater than 65. So I stops here. Now we have to start with J. So what is the value of J? Value of J is 87. So 87 is greater than 65. So there is nothing to do with j because j has to find a smaller element compared to pivot. What is the work of I? I has to find an element that is greater than the pivot. J has to find an element that is less than the pivot, right? So here, since 87 is greater than 65, I just decrement j by 1. So it comes here to this position where what's the value here is 99. It is still greater than 65. So you just decrement. Now here it is 74. 74 is also greater than 65. So you just decrement. Now it is pointing to 94. 94 is also greater than 65. So you just decrement. Now what is the value of j? J is equal to 5. What is the value there? Value is 58 is less than 65. So now j stays in this place. Can we swap I and j? No. Swapping of I and j cannot be done because I value is greater than j. Once when I is greater than j, you cannot swap I and j. If I is greater than j, you have to swap pivot and j, right? That is the only thing you have to remember. So when you do the exchanges, when I value is less than j, right, you have to swap I and j. When I value is greater than j, you cannot swap I and j, provided you have to swap pivot and j, right? So in this case, I is greater than j. I is 6 and j is 5. So I cannot swap I and j, but provided you can swap j and the pivot. So once when you swap j and the pivot, so this is the case. 58 comes to the position of 65, 65 comes to the position of 58. Right? Okay, so now we have sorted elements from 11 to 65. So now, so if you see here, if we take this as the pivot, so the next element is 94. So 94 has to be taken as the pivot now. So what is the position of 94? It is 6. So the lower bound is 6. What is I? We already know I is nothing but increment L by 1. So L plus 1 is L is 6. 6 plus 1 becomes 7. That will be I. And what is J? J is nothing but 9. So same procedure you have to apply here. Increment like I by 1. So first you compare 74 with 94, which is less. Increment I by 1. Now I is pointing to 99. 99 is greater than 94. So I stays in that place. Now what you do is you compare J with. So சொல்லுங்க. இப்போவே சொல்லவா? நீங்க ஆன் பண்றீங்களா? இப்படி ஆயிடும் half an hour. 40 minutes. சரி சார், ஓகே. ஓகே. Right. So we'll come back. So J is pointing to the position 9 where the element is 87. So 87 is less than the pivot 94. So now you compare I and J. I value is less than J, right? I is 8 and J is 9. So you can swap 99 and 87. So 87 comes to this place and 99 moves to 87, right? Now you check out. Right. So now you check out here. Again, you have to iterate the loop I and J and you exchange 94 and 87. So the same procedure you have to follow. Exchange 94 and 87. Right? So again, same procedure you have to follow. Exchange 87 and 74. Right? At last, you will be able to find out the sorted list. I hope that you understood the logic behind quick sort. Okay. Right. So this is the algorithm of quick sort. So as I told you, K is the name of the array, L is the lower bound, lower, and U is the upper bound. So while we begin, what we do, we have to check whether the lower bound is less than the upper bound or not. So why do we verify this is, so at least there should be 2 elements in the array. Only then there is a requirement for sorting. And if there is, for example, only 1 element in the array, so the lower bound will be 0, upper bound will also be 0. In that case, sorting is not required when there is 1 element in the array. So this is the primary thing that we check here is, if lower is less than upper, at least there should be 2 elements in the array. So if the condition is true, we start the sorting process. In that case, as I told you, I will be lower bound plus 1 and J will be upper bound, right? Okay, what is key? Key is nothing but the pivot element. I told you that pivot element is the element available in the zeroth position. So what is lower initially? Lower will be pointing to 0, as I told you in the example before. You can see, just to go through this, right? Okay, lower will be pointing, L is nothing but 0. It is pointing to the first element. So first element will be lower. Right. So K of lower will be nothing but the key. Key is nothing but the pivot element, right? So while what you check is if K of I is less than or equal to key. So I told you that what is the work of I? I has to find out an element that is greater than the key. What is the work of J loop? J has to find an element that is less than the key. If not, you have to, for example, if K of I is less than the key, then you have to just increment I by 1, iterate to the next value and find out whether it is greater or not. Similarly, with respect to J, if K of J is greater than the key value, do nothing with that, just decrement J by 1, right? So this has to iterate. So once the condition becomes true, so what happens, what you have to do, you have to check. I told you that you have to check whether I is less than J or not. So if I is less than J, you have to swap just the values of I and J, increment I by 1, decrement J by 1. Else, if the condition is false, if I is greater than J, that is if I has crossed J, in that case you cannot swap I and J. So in that case, what you do, you just copy the value, that is you just swap J value with the pivot value, right? So where will be the pivot value? It will be in K of lower, right? K of 0, I have selected the initial pivot. K of lower will be the pivot. So you have, in that case, you have to swap J and the pivot, right? So I suppose that you understood the process of quicksort. So to have a quick summary, I can say that quicksort is a partition-based algorithm where first primary thing is you have to select a pivot element, find the exact position of the pivot element on the list. So when you find the exact position of the pivot element on the list, it is nothing but all the elements left side of the pivot element will be less than the pivot element, and all the elements on the right side of the pivot element will be greater than pivot element. So similar process you have to apply for both the partitions until you get the sorted list, right? So next we'll be just looking into the pros and cons of quicksort. So what are the advantages? This algorithm is generally very faster than the most commonly used sorting algorithms, and it also has the best average case behavior. And what's the disadvantages? It uses recursion. So in such a case, the space occupied in this stack, right? The stack space consumption will be quite high. But compared to the other sorting algorithms, we can say that quicksort is better compared to the other algorithms, right? Okay. So now we'll be learning the second algorithm, merge sort, right? Second sorting technique, namely the merge sort. So merge sort is also a divide and conquer algorithm. So here also we roughly divide the given list into equal parts, that is right sublist and left sublist. And finally, we will have to divide the list until a single element is available in the list. And then we'll start to merge the sublist to get the sorted list, right? So this is also a divide and conquer algorithm. So here what we do is we'll first divide the given list into equal parts, which means that you have a left sublist as well as right sublist. Again, further divide the left sublist into equal parts, right sublist into equal parts. So this partition or division has to be done until each sublist has a single element. So once after you divide, then you have to start the merging process. So we'll see how this happens, right? Okay. So we'll take an example of the merge sort here. So assume I have taken this list. So in this list contains 9 elements, totally 9 elements. So the indexing starts from 0 and it goes till 8. So totally there are 9 elements, n equal to 9. Okay. So what's the lower bound here? Lower bound is 0. And what is the upper bound? Upper bound is 8. So the indexing starts from 0 and goes till 8. So lower bound is 0, upper bound is 8. see what happens. So first, I told you that the first primary thing of merge sort is you have to divide this list into equal parts. So how will you divide? If you want to divide the list into equal parts, you have to know the midpoint of the particular index. So how will you find the midpoint as? So it is nothing but lower bound plus upper bound divided by 2. So what is the lower bound here? Lower bound is 0. What is the upper bound? Upper bound is 8. So 0 plus 8 divided by 2, which is 4. So the first partition will have elements from 0 to 4. And the remaining will have elements from 5 to 8. I think you are clear. So here find the midpoint. So it is nothing but 0, 0, that is lower bound value plus upper bound value divided by 2. Lower bound is 0, upper bound is 8 divided by 2. It is 8 by 2, it is nothing but 4. So from 0 to 4 you can partition. It will be partitioned into one list, one sublist, and from 5 to 8 it will be partitioned into other sublist, right? Okay. So now again you find the midpoint. So here if you find the midpoint from 0 to 4, I have a sublist. Again you have to find the partition for this. Again you have to divide this into equal halves, right? So if it is a, for example, if it is a even number of, if n is even number, in this case we have n as 9, right? Totally we have 9 elements in this list. That's why we have 5 in this first part and 4 in the other part. For example, if I have 8 elements, I'll have equal parts. The first part will have 4 elements, right half will also have 4 elements. But in this case, since there are 9 elements, somehow we have to find the midpoint and divide it. So in that case, when I find the midpoint, the first list will have 5 elements, the second list will have 4 elements, right? So similarly, the same partition or division has to be done with respect to all the sublists. So first we'll take this first sublist. So it ranges from 0 to 4. So how will you find the midpoint? It is nothing but lower bound plus upper bound divided by 2. So what is the lower bound here is 0, upper bound is 4. So 0 plus 4 divided by 2, which is nothing but 2. That is, the first partition will have elements from 0 till 2. So 0, 1 and 2 will be in the first partition and 9 and 2 will be in the other partition. Similarly, I have to find the midpoint for the second partition, right side partition. So what is the partition here? 5 to 8, right? 5, 6, 7, 8 is in one partition. Now again, we are going to divide it into sub-partition. So how will you find the midpoint? It is nothing but the lower bound is 5, upper bound is 8. So it is 5 plus 8 divided by 2, which is 13 divided by 2, which is 6 point something, where we'll take the integer part, it is 6. So the index till 6 will be in one partition, remaining will be in the other partition. So 10, that is from starting from 5 to 6 will be in one partition. 7, 8 index, that is element 1 and 12 will be in the other partition. Okay. Again, this you have to continue this process until there is a single element in each partition. So again, take this first partition. What are the elements in this first partition? 0, 1 and 2, right? So what is the lower bound here? 0. What is the upper bound? 2. So 0 plus 2 divided by 2 is nothing but 1. So 0 and 1 will be in the first partition. Remaining element, that is 2, will be in the other partition. So again, we have split this into 2. Again, coming down to this 3 and 4. 3 and 4. I have not written the formula here, but you can understand. 3 and 4. So what is the lower bound in 3 and 4? Lower bound is 3, upper bound is 4. So it is 4 plus 3 divided by 2, which is 7 divided by 2, 3 point something. So 3. So you'll take the integer part alone, 3. So start from 3 and end with 3. So 3 will be in separate partition and the remaining 4 will be in separate partition. Similarly, you have to do with the other two partitions, 5, 6. 5, 6 is together in one partition. Again, we are going to divide it, right? So what is the lower bound here in 5? It is 5. And what is the upper bound? Upper bound is 6. So 6 plus 5 is nothing but 11. 11 divided by 2 is 5 point something. So you take the integer part 5 alone. So start with 5, end with 5. That is till 5 you have one partition. So 10 is separately partitioned, 8 is separately partitioned. Similarly, you have to do with the next list. That is 7 and 8. 7 plus 8 divided by 2, which is 15 by 2, 7 point something. So you take the integer part 7. So start and end with 7. 7 will be in separate partition. 8 element will be in the separate partition. Okay. So if you see this list here, one list still has 2 elements. So you have to again apply partition here for this, right? So when you apply partition for this, so what is the case here? 0, 1 falls in a single list. Again, I have to partition it. So what is 0 plus 1? 0 plus 1 divided. What is the lower bound here? 0. What is the upper bound? 1. So 0 plus 1 divided by 2 is 1 by 2, which is 0.5. So you have to extract only the integer part. So it is 0. So start and end with 0. Start and end with 0. So 15 will be separate, 7 will be separate. Now if you see this, we have partitioned or divided the entire list into small sublists where each sublist has only a single element, right? Each sublist has only a single element. So now we have to see what happens. So I have told you the I have told you the procedure for dividing. So this is how we divide. You find the midpoint, then again partition it. Each partition has to be further partitioned. How do you further partition? Again find the midpoint, and this process should continue until each sublist has a single element. I hope that you can understand. So we'll see what is the procedure for this. So what we do here, again we check a condition. If lower bound is less than the upper bound, I think you can understand what is lower bound. The initial index of the list, that is 0, is the lower bound. And what is the upper bound? The upper index of the list, that is 8, is the upper bound here. So why do we check that lower bound is less than upper bound or not? That is, at least the list should contain 2 elements. For example, if I want to do some sorting, only if there is more than one element, I'll go for sorting. For example, if I have only one element in the list, it is not required to sort. So that's what we check this condition. If lower bound is less than the upper bound, then what we have to do, we have to find the midpoint. I told you how to find the midpoint. Mid is nothing but lower bound plus upper bound divided by 2, as we have discussed in this example, right? Then what we have to do, every partition has to be further partitioned. So what is the first partition here? Merge sort is the procedure. So this is a recursive procedure which will be called again. So first argument specifies the name of the list. What is the second argument? LB, that is lower bound, and it has to go till what? Till mid, right? So initially in the merge sort, we give 3 arguments, name of the list. LB represents the lower bound, UB represents the upper bound. That is the entire list, we give it into the function. Then the particular list will be, we find the midpoint, we divide it into 2 partitions. Now again, you have to apply the algorithm for, you have to divide it for each partition. So what is the first partition? It starts from the lower bound 0 and it goes till the midpoint, right? So what is the midpoint here in the first case? It is 4. So you have to start from 0, go till 4. So that is what is this particular procedure. So what it says, merge sort of A. A is the name of the array or the list. LB is the lower bound and comma mid. That is, you have to take till this and again you have to apply the partition. That is, find the midpoint, and again you have to divide it, right? So this particular procedure, the procedure merge sort, is nothing but name of the array, comma lower bound, comma mid. So you have to write another procedure for the right hand side partition. So I will mention the right hand side partition. For example, 0 to 4 is one partition, 5 to 8 is, so I'm talking about the first partition case. We'll just go through that. 0 to 4 is the first partition, 5 to 8 is the second partition. So I have mentioned that lower bound till mid will be in one partition where you have to further find the midpoint, further divide it. What about 5 to 8? How can you mention 5? 5 can be mentioned as mid plus 1, right? So mid is nothing but 4, mid plus 1 is nothing but 5. So you can start from mid plus 1, go till the upper bound. What is the upper bound? Upper bound is 8. So that's what is the second procedure. So what is the second procedure here? Merge sort of name of the array A, mid plus 1. That is, you start from 5, go till the upper bound. Upper bound is 8, right? So then you have to apply the merge procedure. So when you're doing the merge procedure, you have to start from lower bound. You need the mid value and you need the upper bound. I'll tell you how this works, right? Time being, you have to understand this recursive procedure called merge sort. So first in the merge sort, you'll give the name of the array, the lower bound value and the upper bound value. Lower bound is 0 with respect to this example. Upper bound is 8 with respect to this example. So what you do here, you find the midpoint, you get midpoint as 4. Now what you do, again you have to apply, partition it into 2 and again further partitions has to be done. So you call out this merge sort procedure, name of the array. What is the lower bound here in this example? It is 0. What is the mid value here? It is 4. So you call out that procedure. Again, you find the midpoint and further partitions will go on. Similarly, the right hand side has to be partitioned again. So I told you how to mention the right hand side or the right side partition, which is nothing but mid plus 1. So if the right side partition starts from 5 go till 8. So it is mid plus 1 comma upper bound. So this will be recursively called until, right? So there is a single element in each a single element in each partition. Okay, right. I hope that you understood this process of partitioning or dividing. So you have to find out the midpoint and you have to partition until you get a single element in each list, right? Each sublist. Okay. Next, we'll see how this merging happens. So when you merge, so this is what I have obtained. So you can just go through this. This is what we have obtained after dividing the given list. So we have 15 separately, 7 separately, 5, 9, 2, 10, 8, 1, 2, each in a separate sublist. We'll see how the merging is going to happen. So now you have to start from 0. 0 and 1 will be compared and whichever element is less will be swapped. So when you compare 15 and 7, 7 is less than 15. So you have to make this swapping here. So 7 and 15. And you have to put it in a single list, right? So both 15 is in separate sublist, 7 is in separate sublist. So what you have to do is take two adjacent elements. What we'll do, compare it and you put it in a same list. Okay, so when you compare 15 and 7, 7 is less than 15. So you just put it in a same list. Now you take the next adjacent element. So what is the next adjacent element? It is 5. Now you have to compare 5 with 7 and 15. So in this case, 5 is less than 7 and 15. So you have to formulate a list, put 5 in the first place, then comes 7 and then 15. Okay, now what you have to do, you have to compare the next two adjacent elements. So 9 and 2. In this case, 2 is less than 9. So you have to swap and put it in a single list. Now this list has to be compared with the previous list. And we find that 2 is less and which comes in this place. Then comes 5. So you have to arrange it in sorted order. Then comes the right side partition. Again 10 and 8. Compare it. 8 is less than 10. Right? So you just swap it, put it in a single list. Compare 1 and 12 where 1 is less than 12. So it is exactly in that position but put it in a single list. Now compare this two, you sort it, you get a list. Finally, this list will be compared with this list and you find out the sorted list. Right? So now we'll see how this merging process works with respect to the algorithm. Right? Okay. So here I'll just take this last few steps. I'll explain you how the merging part works, right? So this is the pseudocode for merging. I'll tell you how this works. So I have taken this last part which I've shown you in the previous page. So this is what is happening. I get a sorted list at the end, and previous two steps I have taken, I put up in this page. I'll tell you how this works, right? Okay. So we'll see this how this merging process works. So initially, where should I keep this I? I is nothing but it has to point to the 0th position. So what is there in the 0th position? I refer it as lower bound. And what is the upper bound here? Upper bound is 8. That is the last index is called the upper bound. So upper bound is 8 and lower bound is 0. So initially, I will be pointing to the lower bound. That is there in the pseudocode, right? I will be pointing to the lower bound. And what is upper bound? Upper bound is 8. Okay, right. Now what is j? J is going to point to the first element of partition 2. So I is going to point to the first element of partition 1 and j is going to point to the first element of partition 2. So I is pointing to element 2 and j is pointing to element 1. Okay, right. So this is lower bound is 0. What is the mid value here? Mid is 4. What is mid plus 1? Mid plus 1 is 5, where I have to make the j point to it. So see the pseudocode now. So lower I is nothing but it is the value of lower bound, which is 0. So it is indexed to 0. What is j? J has to point to the second partition. Where does the second partition starts? It starts from 5, which is nothing but mid plus 1, because mid is 4. 5 is mid plus 1. So mid plus 1 is j. right? So L is nothing but the variable which I have created to point to the initial position of a temporary variable. So we are going to create a new temporary array where you are going to place, or new temporary list where you are going to place the sorted elements, right? Okay. So now what we have to do is you have to compare the value of I and j. Okay. So why do we make this comparison? For example, when I compare all the elements of I and at last I find that I have ended up the first partition, in that case you have to stop the comparison. You have to like copy every element of J to the sorted list. On the other contrary, right? So for example, I have read every element from J and there are still elements in I. Then what you have to do? You have to stop the comparison process, take every element of I and put it in the sorted list, right? So now we'll come to this comparison. See here. So what is in K of I? K of I is nothing but 2. எடுத்துட்டீங்களா? இன்னொரு 5 minutes ஆகும், நீங்க சொல்லிடுறீங்களா? போட்டுருங்க. சொல்லவா? சரி. Okay, okay. Okay, sir. Okay. Okay, so I'll be continuing class. Meanwhile, you can just post your feedbacks. You can post your feedbacks. I'll continue the class. Right, you can post your feedbacks. I can resume it back. Okay, so we'll come back to this part of the algorithm. So if you see here, just a minute. Right. So we see here, you have to compare the I value with the j value. So what is in K of I? K of I, the value is 2. Right. And K of j, the value is 1. So you have to compare K of I with K of j. So whatever be the smallest element, you have to place it in the new array called temp. Right. So whatever be the smallest element, you have to place it in the new array called temp. So in this case, if you see, I value is greater than j value. So that is 2 is greater than 1. So 1 has to be copied to the temporary variable array, right? So you copy 1 to this temp array. Okay. So you have to copy the value of I to the temp array. Okay. And you have to move the pointer right by 1 position. So that's what is there in the pseudocode. You can just check it out. So if k value is k of I is less than k of j, then you have to copy the value of I to the temporary variable and increment I by 1 and also L by 1. Else If k of I is greater than k of j, then what you have to do? You have to copy the j value and place it in the temp variable and temp array, and you have to increment j by 1 as well as L by 1. So in this first case, what we have done is we have combined the I value with j value, that is 2 is greater than 1. So you have to copy the value 1 to this new temporary array. So we have copied 1 to this position of the temp array, and you increment L by 1, right? And also you increment j by 1. Now j is pointing to 8 and I is pointing to 2. So you compare again I and j. So what is the value of I? Value of I is 2 and value of j is 8. So 2 is less than 8. So in that case, you have to copy 2 to the new temp array. So I have copied 2 to this array. So once when you copy 2, it is indexed by I. So what you have to do, you have to increment I by 1. So increment I by 1 and also L by 1. So increment L by 1, also I by 1. Okay, now I is pointing to 5 and j is pointing to 8. So now compare both. So which value is less? 5 is less than 8. So in this case, copy 5 to this new temp array. Okay, increment L by 1 and also I by 1. Okay, right. Now again compare I with j. So 7 is less than 8. So copy 7 here, increment L by 1, also I by 1. Now again compare 8 and 9. So which is less? 8 is less. So copy 8 here, increment L by 1 and also j by 1. Now again you have to compare. I is pointing to 9, j is pointing to 10. So compare 9 and 10. 9 is less. Copy 9 here, increment L by 1, I by 1 here. Okay, the same procedure continues and you will be able to get the sorted list. Okay. So finally, we'll be able to get the sorted list. Okay. So one more condition that you have to remember is, so when you are iterating the I variable, so for example, if I is greater than the upper bound, so, or in this case, I is greater than the mid value, that is, assume that I have reached 4 and still more elements are available in J. So it's not required to compare any element of J with I because I have reached the end of I. So in that case, what we have to do is, you have to just copy the value of J into the temp. That's what is this particular part of the pseudo code. So if I is greater than the mid, which means I have reached the end of the first partition, and assume that I have here 5 elements, but assume that in J I have 7 elements. So and in I have only 5 elements. So assume all the 5 I have copied to my new array, and still 2 more elements are available in J, or still 3 or 4 elements are available in J. So if I have completed all the elements in I and still I have more elements in J to be copied, it's not required for a comparison. In that case, simply you can copy the elements of J to the temporary array. Similarly, vice versa, while I is less than or equal to mid, or on the other contrary, for example, J has reached the end of the array and still some elements are available in I. It's not required to compare again, just copy the remaining elements to the array. So this part of the pseudocode tells you that. Okay, you can just go through it. And concerned with the pros and cons of this particular method, advantages, it is very useful for sorting bigger lists, and you can also apply this for external sorting. The main drawbacks of this include it needs a temporary array every time for storing a new sorted list. Hope you understood this approach on merge sort. So the simple thing you have to remember is, it's divide and conquer method. You have to divide and partition the given list into smaller sublists such that each sublist contains only one element. Then you have to apply the merging process and merge the list to find out the sorted element. Thank you everyone for listening to this session. Hope you understood both the sorting approaches in detail. Thank you. சார் முடிச்சிச்சு. ஸ்டாப் பண்ணிட்டீங்களா? எடுத்துட்டேன் சார், எடுத்துட்டேன். ஓகே ஓகே சார்.